Greetings. Today we're going to take a look at the rational roots theorem, which is an excellent way of dealing with higher degree polynomials larger than the quadratics you might already be used to. The main idea of this theorem is that if you've got any polynomial, as long as it's got these real valued whole number coefficients, if that polynomial has any rational roots, roots in the sense of numbers that make the whole thing turn into zero, if it has any rational roots, they have to be of this format. Any roots that can be written as a fraction have to be plus or minus a factor of this last constant here over a factor of this first coefficient. Those are the only possible rational roots. Of course, there may be irrational roots. The polynomial might not even have any rational roots. They might all be irrational. But if it has any rational roots whatsoever, they have to be of this format. The main advantage of this is that it allows us to make a list of the possible rational roots and then test all of them out. For example, in this sample quartic here, fourth degree polynomial, the last number, 12, and the first coefficient, 3, we can factor those to get an idea of the possible roots of this quartic. For example, factors of 12, only possibilities are 1, 2, 3, 4, 6, and 12. So those are all the possible numerators. Factors of 3 are just 1 and 3. Those are all the possible denominators. So our list of possible roots has to be a numerator from this group over a denominator from this group. In other words, every single one of these over 1, and every single one of these over 3. Of course, some of these are repeats. For instance, 12 thirds is 4, and we've already covered that. 6 thirds is 2, and we've already covered that. 3 thirds is 1, and we've already covered that. So the actual list we're dealing with is going to be 1, 2, 3, 4, 6, 12, 1 third, 2 thirds, and 4 thirds. And of course, there's a blanket plus or minus on that whole thing as well. So, this is still a fairly big list. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, doubled because it's plus or minus 18 possible rational roots. But that's still a marked improvement over the infinitely many possibilities we'd have without the rational roots theorem. We don't want to just start plugging in numbers without having any place to start. This gives us a starting point. We can try each of these numbers in turn in this polynomial and see if any of those result in 0. So let's try that out. Given this list of possible x values, we'll plug them in one at a time and see if any of them make the whole thing turn into 0. Starting with the easiest one, 1. If we just plug in 1 for x, all of these x to any power just become 1. So we get 3 times 1 plus 10 times 1 minus 9 times 1 minus 40 times 1 minus 12 times 1. And that doesn't look like it's going to be anywhere near 0, because the positives, 13, the negatives are way less than negative 13. So there's no way these are going to cancel out. So x equals 1 does not work. Let's try the next one. If we try negative 1. We plug in negative 1 to any odd power will be negative 1. Negative 1 to any even power will be positive 1. So all the even powers become positive 1. All the odd powers become just the opposite. 40 times negative 1 becomes negative 40. Subtracting negative 40 is adding 40. And so on. Do those add up to 0? We got negative 19. And a negative 12 makes for negative 33, which isn't enough to cancel out the positive 43. So negative 1 also does not work. We know x is not 1, x is not negative 1. Let's move on to 2. See if 2 works. Let x equal 2. We got 3 times 2 to the 4th would be 2, 4, 8, 16. So 3 times 16. 10 times 2 cubed would be 8. Minus 9 times 4. Minus 40 times 2. minus 12. 3 times 16 is 48, plus 80, minus 36, minus 80, minus 12. And let's see what happens to those. The 80s cancel out, that's convenient. Negative 36 and negative 12 makes for negative 48, which cancels out the 48, and we get 0. So that means we found a root. 2 works. X equals 2 is a root. And anytime you've got a root, you can also immediately find a factor. If 2 is a root, then x minus 2 is a factor of the polynomial. Which means we can factor it out. So let's try factoring out x minus 2. We know that this polynomial can be written as x minus 2 times something. We don't know what that something is, but we can find it. The reason x minus 2 has to be a factor is we know that plugging in 2 for x turns the whole thing into 0. In this factor, plugging in 2 for x means you get 2 minus 2, that's 0. 0 times anything becomes 0. So in general, if you have a factor, then if you have a root, then x minus that root is a factor of the polynomial. To find what's left, we know that something times x minus 2 equals the quartic. So we can divide by x minus 2 to cancel it out and figure out what that something is. So let's try that. If we want to know this polynomial divided by x minus 2, we can work that out with long division. And long division with polynomials works exactly like long division with ordinary numbers, except different. Instead of having a ones place, a tens place, a hundreds place, a thousands place, and so on, we've got a ones place, an x squared place, an x cubed place, and an x to the 4th place. We want to divide that whole thing by x minus 2. So we ask ourselves, x times what would be 3x to the 4th? For that we're going to need a 3x cubed, because 3x cubed times another x becomes the 3x to the 4th we want. Of course, we also have this minus 2. We multiply that by 3x to the 3rd also. We get minus 6x cubed. We want to subtract that from what we have to see what's left. The 3x to the 4ths cancel out, which they should. 10x cubed minus 6x cubed becomes positive 16x cubed. Bring down the next term. And we ask ourselves, what times x would be 16x cubed? For that, we'll need a 16x squared. That times x minus 2 would be 16x cubed minus 32x squared. Subtract that whole thing. The x cubed terms cancel out. Negative 9x squared plus 32x squared becomes 23x squared. Bring down the next term. And what times x would be 23x squared? For that, we'll need a 23x. Times x becomes 23x squared. 23x times minus 2 becomes minus 46x. Subtract to see what's left. We get positive 6x. Bring down the next term, and this is looking good because 6x requires a 6 times x. The 6 times minus 2 becomes minus 12. Subtract those, we get 0 remainder. That means that, yes, x minus 2 really does divide this evenly, and this cubic is exactly what's left. We now know the other factor. 3x cubed plus 16x squared plus 23x plus 6. So we have factored the quartic into a single binomial times a cubic function. And the great thing about this process is it's repeatable. We can apply the same idea to this cubic to split out another factor. So let's try that again. Applying the rational roots theorem once more, we are looking for factors of the final constant divided by factors of the first coefficient. So that will be factors of 6 become 1, 2, 3, 6. And we could have each of those divided by either 3 or 1, because those are the factors of 3. So we've got 1, 2, 3, and 6 divided by 1, and 1, 2, 3, and 6 divided by 3. And of course, 3/3 is 1, and we already have that. 6/3 is 2, and we already have that. So we can skip those. And we're left with just 1, 2, 3, 6, 1/3, 2/3, and again, a plus or minus. So a much shorter list than before. Furthermore, we already checked plus or minus 1 and found that neither of those work, so we can rule that out. We already checked positive 2, but that worked, but it's possible that it might work again. 2 might be a repeated factor, a repeated root. So we should try that again. Let's try x equals 2 again, plugging into this cubic. 3 times 2 cubed, 16 times 2 squared. Hold on a minute. 2 to any power is going to be positive. These terms are all being added. We know that we're never going to get to 0 by adding positives to more positives. So that suggests we can skip positive 2 entirely. In fact, we can skip all of the positives from this point onward. We know that this positive coefficient cubic has no positive roots, only negative roots. So let's try negative 2 and see if that works and move on from there. Negative 2 is going to be the same absolute values. We'll just have negative signs on all of the odd roots. So 3 times negative 2 cubed becomes 3 times negative 8. Then 16 times positive 4. 23 times negative 2. And plus 6. That gets us negative 24. Positive 64. Negative 46. And 6. I'm noticing these combine to positive 40, these combine to negative 40. Those are going to cancel out, which means x equals negative 2 is another root. X equals negative 2 is a root. So that means x minus negative 2, in other words x plus 2, must be a factor. So we can divide x plus 2 out of this cubic. And we could use the long division method we looked at earlier, or alternatively, another way we can divide a polynomial or factor a polynomial that's sometimes easier to visualize is the rectangle method. What we can do is we can draw a rectangle, and we know we want a binomial, x plus 2. So if you imagine this length is x and this is an extra length 2, and we want to multiply that by something to get a cubic. We factor a first degree binomial out of a cubic, we should be left with a quadratic. So we should expect an x squared term, an x term, and a constant term. And that should be it. So let's see what works. We know we need a 3x cubed here. 3x cubed, the only way to get 3x cubed from this x is by multiplying by 3x squared. But of course, this width has to be represented by this entire height, including the plus 2. So 3x squared combines with the times 2 to get 6x squared. Of course, we don't want a 6x squared, we want a 16x squared. We've already used up 6x squared, so we need an extra 10x squared here. Of course, to get that, we need to multiply x by 10x. But that 10x, of course, also multiplies by the 2 to get 20x. But we don't want 20x, we want 23x. 20x is already taken care of, so we need an extra 3x. That'll go here. To get 3x from x, we need to multiply by 3. The 3 multiplies by the 2 as well to get 6, which is exactly what we need. This method is entirely equivalent to the long division method, just a more visual way of writing it. And we now know that this factors into x plus 2 times this quadratic. 3x squared plus 10x plus 3. And of course there's also the x minus 2 that we already factored out. So we've now split the quartic into 2 binomials multiplied together and multiplied by this quadratic. And you could keep this approach going further, applying the rational roots theorem to this quadratic. But we already know how to deal with quadratics. We can just factor this quadratic by any method you want, use a generic rectangle or a magic square or whatever they're calling it these days, or you can use the quadratic formula. In fact, if there are no more rational roots, even if this has irrational roots or imaginary roots, the quadratic formula will take care of that. But I think this one should be factorable. Let's try using the generic rectangle approach. We want 3x squared plus 10x plus 3. So this one, if it's rational, clearly has to be a 3x and an x. And 3, if we want rationals, these are going to have to be 1 and 3. Now I know plus 1 isn't going to work because we already ruled out 1 and negative 1. So let's put a plus 3 here and a plus 1 here. Those multiply to 3 and see if it works. 3x times 3, 9x. 1 times x, 1x. Those do add up to 10x, so this checks out. The quadratic factors 2, x plus 3 times 3x plus 1. And then we still have the x plus 2 and the x minus 2. So now this is completely factored. And we can see that the roots are 2, negative 3, and negative 1/3. And this approach should work for any polynomial. No matter how high the degree is, as long as it has rational roots, this approach will find those rational roots and you can factor out the associated factors. As long as it has no more than 2 irrational roots, you can get it down to a quadratic, and then the quadratic, you can just apply the quadratic formula. So make up some examples, try it out on your own. And until next time, learn from the past, reach for the future, and together we can build a better world.